We're going to look at using cylindrical coordinates as one possible way of extending polar coordinates to 3 dimensions. There are also other ways to extend polar coordinates to 3 dimensions, but for this video we're going to look at cylindrical coordinates. So before we get into cylindrical coordinates, let's just think a little bit about rectangular coordinates and what that means and what those numbers are in 3 dimensions. So in rectangular coordinates we've got ordered triples x, y, z, and we know that if we have some numbers, say 1, 2, 3 in an ordered triple, and we know we're in rectangular coordinates, we know what those numbers are telling us, that we've got a point, and from the origin we're going to go 1 unit in the direction of the positive x-axis. So from the origin we're going to go out 1 unit, and then we're going to go right, or in the direction of the positive y-axis, 2 units, and then we're going to go 3 units in the direction of the positive z-axis. So that would be up, the way I have my axes oriented. And so that gives us the location of a point where we end up. It's also important to notice that whatever order you happen to do those coordinates in, it doesn't really matter as long as you do each one what it's telling you to do. So for example, I could start at the origin and I could go 3 units up, and then 2 units over, and then 1 unit forward, and if my scale was perfect on my axes here, we should end up at exactly the same place, even if I did those in a different order. So that's given us the location of a point. So in cylindrical coordinates, we also have ordered triples, and so the numbers in the ordered triple, though, correspond to values r, theta, and z. So let's start with the one that's easiest to understand. Z is really just the same z as rectangular coordinates. That's a distance in the parallel to the z-axis, so up or down, the way I have my axes oriented, from the xy plane. Alright, so that would be, if you're at the origin, a distance up or down, or any place else in the xy plane, that same z distance up or down. Okay, so that's really just the same as rectangular coordinates. R is, just like in polar coordinates, a radius. And in polar coordinates, our radius is measured outward from the origin. So just two-dimensional polar coordinates, we measure that outward from the origin. So r equals 0 is at the origin, and then larger r values are just coming out from the origin in different directions. You can have negative r values too, so at a particular theta, you would have that theta, and then you go backwards to the origin. So that's a radius. In 3 dimensions, it's still a radius, and in the xy plane, that's going to be the same as what we have in polar coordinates, so outward from the origin. But remember that we also have this z value, so we could be up at some other level if we already had gone up or down some z value, and then we'd measure that radius from there parallel to the xy plane. So this is a radius measured really from the z-axis, and we measure that radius parallel to the xy plane. So we talked about in rectangular coordinates, it doesn't matter what order you think about those in as you plot that point. I tend to like to do my radius in the xy plane and then go up or down z, whatever the z coordinate is. And for theta, that is also just like polar coordinates in the xy plane. So let me just draw a little two-dimensional picture here in the xy plane. When we think about an angle theta, we think about that as a rotation from the positive x-axis toward the positive y-axis. And then whatever the r value is, we end up forward or backward along that theta. So in cylindrical coordinates in 3 dimensions, it's the same. It's a rotation. And so that would be from the positive x-axis toward the positive y-axis. But when you're in 3 dimensions, remember that you might be up or down some z level. So if you're in the xy plane and you rotate around some theta, whatever that would be, but if you've already gone up or down some z level, then you can also have that same rotation. So it's really an angle of rotation from the positive x part, positive xz plane, toward the positive y plane. So we can think about that almost like a door opening up on a hinge. So from the positive xz plane to toward the positive yz plane. So the same polar coordinates, just extended up and down. All right, one other important thing, so you know some conversion formulas between xy coordinates and polar coordinates. You need some conversion formulas between cylindrical and rectangular coordinates as well. So fortunately, you already know these. Really, you're just converting the xy to polar. So x is our cosine theta, y is our sine theta, and x squared plus y squared equals r squared. When we get to the point of doing integration in cylindrical coordinates, you're going to need to think about your differential. So you know that when you do double integrals, your dA in polar coordinates has r dr d theta. So when you do in triple integrals, the z is going to be ordinary, so you're going to have a dz for that part, but you're going to have this extra r that you get for polar coordinates as part of your differential for cylindrical coordinates. So you're going to have that extra r. And then dz dr d theta, and that dz dr d theta could be in whatever order is appropriate depending on if the region is z simple, r simple, or theta simple. All right, so let's go ahead and look at some examples using cylindrical coordinates. So for these problems, we're going to just plot some points that are given in cylindrical coordinates. So it would be important to remember that these are r, theta, z values. So you're clear about what's the r, what's the theta, and what's the z value. So I'm just going to set up a xyz coordinate system here, and I'm going to go ahead and label my axes. As usual. All right, so I want to think about plotting this point. I tend to like to do my theta first and then do my r and my z values. So if I am in the xy plane and I do my theta is pi, let me just draw a little two-dimensional picture over here of that. So if I'm in the xy plane and I do theta equals pi, I'm rotating over to the negative part of the x-axis. So in R3, I need to extend my x-axis so it'll be negative there. And I'm just going to rotate in the xy plane around to the negative part of my x-axis, from the positive x-axis toward the positive y-axis, and then back to the negative part of the x-axis. All right, so that's my theta. And then from there, I want to think about along that axis going out 2 units. So I need some sort of scale here. So on that axis, I'm going to go out 2 units. So in the xy plane, I rotate around pi and then go out 2 units. I'm here on the negative part of the x-axis at negative 2 units on the back end of the x-axis here. All right, and then I want to do my z-coordinates, so I need some scale in my z direction here. So from that point where I rotated around pi, went back 2, then I'm going to go ahead and go parallel to my z-axis, about that same distance there. And then there's going to be my point A, and that point A is going to be in the xz plane above the negative part of the x-axis. All right, for point B here, I'll just do that one in a different color. So if I think about that theta rotating around pi over 2 just in 2 dimensions, that's going to be from the positive x-axis toward the positive y-axis. So you'll end up on the positive part of the y-axis. I'm going to rotate around pi over 2. And then on that axis, I'm going to go out 1 unit. So I need a scale there. So out 1 unit from the origin in there. So I'm at 1 unit over on the positive y-axis at that point. And then from there, I'm going to go down 3 in the z direction. So I'll just put a scale on my axes there and then go down 3. So my point B here is 3 units below the xy plane. So it's in the yz plane, 3 units below the xy plane. All right, so when I think about pi over 4, just in 2 dimensions, I'm rotating around 45 degrees from the positive x-axis toward the positive y-axis. So I'm going to have to kind of be a little careful here in my picture, partly because I have a lot of stuff on here already, but I'm just going to have to kind of estimate where that would be. So it would be along the line y equals x in the xy plane, pi over 4. And then the radius is 0. So if I go back over here to my xy plane and think about radius 0, you're going to be at the origin. And one important thing to notice about that, even just in the xy plane, is that no matter what that theta is, if your radius is 0, you're going to be at the same point, right? If r equals 0, you're going to be at the origin no matter what that theta value is. So I'm going to be at the origin in the xy plane and then down 2 units. So that point C will be on the negative part of the z-axis. Okay, so a couple of important things related to that example. One of them is that, especially with this point C, you can kind of see that, but you can also think about it with some of these other points as well, is that each point does not necessarily have a unique ordered triple. So each point or location does not have a unique ordered triple in cylindrical coordinates that describes that point, right? So particularly with that point C, you can see that you would use different theta values and you'd still be at the same point. But even for the other points, you can think about that there would be other angles that are coterminal with that. So for example, our point B, I could have an angle of perhaps negative 3 pi over 2. That would put you at the same angle. You can also have an angle that rotates around to a different point and then use a negative r value to get to those same points. So that's an important thing that we will sometimes exploit. One other important thing about these examples is that you might notice that I don't actually need any negative r values. I can use them if they're convenient, but I really only need r values that are greater than or equal to 0 and theta values that are between 0 and 2 pi. And I don't actually even need both theta and 2 pi, just one or the other of those in order to cover all of R3. Z, of course, you would need all real numbers for that because you can go up and down forever. All right, so sometimes we will exploit that when we do some problems using that. All right, let's look at a couple more examples. All right, so for these two examples, we're going to take these equations of surfaces that are in rectangular coordinates and convert them to polar coordinates. So in essence, you're just doing the same conversion formulas that you use to convert between rectangular and polar. So you would notice that you have x squared plus y squared, so you could rewrite that as r squared minus z equals 4. So that's it. That's just converting that to cylindrical coordinates. We might think just for a second about what this graph looks like, just to get a little more comfortable thinking about graphs in cylindrical coordinates. I'm going to graph the rectangular coordinate form just because you're probably more comfortable with that. So if I do a little rearranging of that rectangular coordinate form, subtract 4 from both sides and add z to both sides, I get it in this form, which is maybe a little bit easier to see what this is. This is a paraboloid. The traces in the yz plane and the xz plane are parabolas that intersect the z-axis at -4 and open up. And then the trace in the xy plane, when z equals 0, is a circle of radius 2. So this is a circular paraboloid. I'll just do a little rough sketch here. Circular paraboloid, that circle in the xy plane is x squared plus y squared equals 4 is the trace in the xy plane. So not all paraboloids are really nice or simple equations in cylindrical coordinates, but the key thing is that the z would be like ordinary rectangular coordinates, and then you have circles that are in the xy plane. So circles in the xy plane or parallel to the xy plane are equations that are generally pretty simple in cylindrical coordinates. All right, this other one here, we're going to go ahead and convert that. So I don't have an x squared plus y squared that I can convert to r squared, but we do know that x is r cosine theta, so we can just make that substitution. And at that point, I've converted it. If you want to solve it for r, you could maybe divide both sides through by cosine theta, and you could write that as r equals 3 secant theta. You might see it written like that sometimes. And so why you might want to do that is if you're setting up some integration or something like that using cylindrical coordinates. Let's just think for a second about what that graph looks like. Again, it's easier to think about in rectangular coordinates because you're more comfortable with that. So that's really a plane that's parallel to the YZ plane. I just drew a little part of it there, just a little sketch. Plane out at x equals 3 and then parallel to the YZ plane. So just a couple of kind of simple conversions there. Nothing really new, it's just you're using your polar coordinate conversion formulas. Okay, in these examples, we're going to look at graphing some surfaces in cylindrical coordinates. So these are all equations that are really simple equations in cylindrical coordinates, and so it's kind of helpful to be able to recognize what these graphs look like. So these should be pretty easy. The Z1 is going to just be what you normally would think of when Z equals 3. So you're up here at Z equals 3, and then in rectangular coordinates, your X and Y are just going to be all real numbers. Or in polar coordinates, cylindrical coordinates, when you're up here at Z equals 3, your R can be all different values, and your theta can be all different values, but you still end up with this plane that's parallel to the XY plane. So that's the same graph as if that equation were given in rectangular coordinates. It only involves Z, and Z is the same in rectangular coordinates. All right, R equals 3. I'm going to do a little two-dimensional picture here of R equals 3 just in the XY plane in polar coordinates. And so hopefully you recognize that. If you just think about what R represents in polar coordinates, it's a radius. So that's a circle of radius 3 in the XY plane. In cylindrical coordinates, in 3 dimensions, I have that circle, r equals 3, in the xy plane. But then z is unrestricted by this equation. Z can be all real numbers, so there's my little circle in the xy plane. But then since z is unrestricted, z can be all real numbers, so it's going to extend up and down parallel to the z-axis. So we've got a circular cylinder of radius 3, and it extends in the z direction along the z-axis. All right, this next one, we can also think about that graph by thinking about a little two-dimensional picture just in the xy plane to start with. So just in polar coordinates, if you think about theta equals pi over 3, you're going to rotate around pi over 3, and then r can be all real numbers, positive and negative, so you get a line in the xy plane in polar coordinates. And then when you think about in cylindrical coordinates in 3 dimensions, you're going to start with that line in the xy plane. So I've just rotated around pi over 3 radians from the positive x-axis toward the positive y-axis. And then r can be all real numbers forward and backward. And then in 3 dimensions, z can also be all real numbers, so that's unrestricted. So we're going to just take that line and extend it up and down the z-axis. So both up and down. So that's also a plane. That plane contains the z-axis, almost like if there were a door hinged on the z-axis and it just kind of rotates there on that z-axis. That's what that plane is. All right, this next one's a little harder because it's not just a single variable. It's got z and r, so I can't just think about it in 2 dimensions. So I'm going to go ahead and convert this one to rectangular coordinates with the hope that maybe you recognize it as one that we've done before. So if you just think about your conversion formulas, x equals r cosine theta, y equals r sine theta, x squared plus y squared equals r squared. None of those are immediately obvious, but you might notice that if you square both sides of this, if z equals r, then squaring both sides preserves that equality, so z squared equals r squared, and then you can substitute in for the r squared, so you get x squared plus y squared. All right, so that one is in rectangular coordinates, z squared equals x squared plus y squared. Maybe you recognize that as the equation of a cone. The traces in the xz plane and the yz plane are lines. z equals plus or minus x, and z equals plus or minus y. So those are lines that form 45-degree angles with the coordinate axes. And then when z is 0, you just get the point at the origin. And when z is bigger or smaller than 0, you get circles up at higher and lower levels of z. So this is a circular cone, and it opens on the z-axis. Right, and so if you think about that in terms of cylindrical coordinates, when z equals 0, you're at r equals 0, which would be at the origin. And then when z is bigger, say z equals 1, so you're up at a height of z equals 1, and then you get a circle of radius 1. So you get all these circular cross sections that are getting wider and wider as you go up. All right, so either way, you can think about that as a cone. It's really both halves of the cone. If you want to restrict yourself to, say, z values that are greater than or equal to 0, that would be the top half of the cone, where z and r are both greater than or equal to 0. And then the bottom part of the cone, so from the origin down, would be where the z values and the r values are less than or equal to 0. So remember, z equals r. So if z is less than or equal to 0, r is less than or equal to 0 as well. All right, so we're going to look at some more videos with some integration problems with cylindrical coordinates, so you can look at those next.